Hi there. In this video I'm just going to go through the basics of the three tactics: intro, apply and exact. There's not going to be any spoilers in this video. Here's the course notes, and you can see intro, apply and exact are three tactics which are now documented in part C. Part C is the tactics part of the course notes, and there's an explanation of what exact does. I've added a tactic cheat sheet, and I've also I thought I'd also added a link to the community website, but I've failed to push that to the internet. Hard luck. There's also supposed to be a link to the let me just show you while I'm here. What's it called? Lean Prover Community. Let's go here. By the time you watch this, there'll probably be a link to this page here. There we go. This is actually all of Lean's tactics as documented on the Lean community website. So if you want to see somebody else's take on what tactics do, you can look here. But let's get on with what I want to talk to you about today, which is using, a basic overview of what a little puzzle looks like in the Lean Theorem Prover, and how to solve them with some basic tactics. So here is Visual Studio Code, and the thing you always have to remember is you need to open the folder. I'm going to click on Open Folder, and now where are my Lean projects? My Lean projects are here, and Formalising Mathematics 2022 is here, so we go there, and hopefully there it all is. Great. So here's sheet 1. Let's put that over there, and let's make this a bit smaller. So I'm going to go through the worked examples. You see explained here that to solve these, there's some puzzles here, and to solve these puzzles you need to know how those three tactics worked. And you can read about how they work in the course notes, but I'm just going to show you how they work here by example. So what have we got here? We've got throughout the sheet, P, Q and R are going to denote propositions, true, false statements, also throughout the course notes as well. I'm using capital P, capital Q and capital R to denote true, false statements. So let's delete this one here. Let's go through this worked example here. So this example here says we've got hypothesis HP, which says that P is true, and hypothesis HQ, which says that Q is true, and hypothesis HR, which says that R is true. And then we've got a colon, and after the colon is the thing we have to prove. So let's look over here on the right hand side here. We can see Lean's brain. So Lean's brain says that P, Q and R are propositions. HP is the hypothesis that P is true. HQ is a proof of Q, and HR is a proof of R. And we're expected to prove that P is true. We're expected to deduce P from our hypotheses. Well, of course, one of the hypotheses is that P is true. This HP colon P means that HP is a proof of P, or HP is the hypothesis that P is true. So the tactic we want here, you see our goal here is exactly, one of our hypotheses is exactly hypothesis HP. So we're going to put exact HP. And when we do that, it says goals accomplished. And it also says that we have an error. And the error is we're apologising for no reason. There are no goals to be solved. So let's delete that there. And you can see down here that you see we have, I'm always looking down the bottom here. This little X, you see this blue line at the bottom. We have sort of a cross and a circle, and then it says 0. That means there's no errors. But the exclamation mark in a triangle, it says 11, so it says there's 11 warnings. But I should, before we'd solved this one, there, you see there were 12 warnings, and once we solve this level, exact HP, it goes down to 11 warnings. So again, let me just delete, this is one of the worked examples, let me just get rid of this and put sorry. And now you see we're back down to 12 warnings. I mean, if I remove the sorry, then you get an error, right? If you don't if you finish your proof and you haven't actually proved it, you see that you get this error over here. There are unsolved goals, and we have one error. So to make Lean stop complaining about the errors, we put sorry, and now it just gives us a warning that a warning just means you're cheating, right? So let's have a look at this goal here. This goal here says P and Q are true false statements. We have a hypothesis HQ. The hypothesis is that Q is true, and we've got to prove that P implies Q. So if you want to think about it in terms of truth tables, we're saying whatever P is, it implies a true statement. So we're saying that true implies true and that false implies true. And both of those are indeed true. So this goal should certainly be true, but we're going to prove it kind of constructively. We're going to prove it using intro, exact and apply. So let me show you a constructive proof of this thing. We've got to prove that P implies Q. So that means, what does P implies Q mean? It means that if we assume P, we can deduce Q, right? So let's assume P, and that's intro whatever, intro fish. There. Now we've labelled the hypothesis fish. This hypothesis fish says that P is true. I mean, that's not the best name for hypothesis that P is true. I would normally use the hypothesis HP. But what my point is that you don't have to call the hypothesis anything related to what it's a hypothesis about. We can call it anything. So intro fish. And now our goal has changed to Q. Now we've got to prove that Q is true, but that's one of the hypotheses. That's hypothesis HQ. So we can do exact HQ. So there we go. And then goals accomplished. And now delete the sorry. And I'm deleting lines by doing Control X. By the way, Control X deletes the line you're on. So there we go. Now we're back to 11, and now we're back to 11 warnings. So again, let's just delete this worked example. Let's replace it with a sorry. So now we're up to 12 warnings again. And how are we going to do this one? Well, this one, we have a hypothesis that P implies Q, and we have a hypothesis that P is true, and we need to deduce that Q is true. So there you go. Isn't that modus ponens or something? I think the logicians call that. And what we're going to do is we're going to do this backwards, right? Normally, a mathematician might say, well, we've got the hypothesis that P is true, and we've got the hypothesis that P implies Q, and so we're going to deduce that Q is true. But I'm not going to do that. And then, of course, once we've deduced the Q, I mean, I'll show you how we can do that in Lean. Let me go have HQ, Q, and that would be HP. So this would be arguing forwards. This is not what I'm going to be teaching you in this problem sheet. I'm just saying that it can be done. And now we've got this hypothesis HQ. We can do exact HQ. And there we go, goals accomplished. So that is one way of doing it, arguing forwards. But the apply tactic argues backwards. So what's going on here? We're trying to prove that Q is true, but we know that P implies Q. So it would suffice to prove that P is true, right? If we can prove that P is true, then we can deduce that Q is true. And if we can deduce that Q is true, then we've solved the level. And so what the apply tactic does is it argues backwards. You see, the goal has changed, right? The goal used to be Q. None of the hypotheses have changed, but the goal has changed. It's changed. It used to be Q, and now it's P. So that's what apply does. It kind of does the last step of the proof. Well, P implies Q, and so if we can prove P, we can deduce Q. And so that's this, if you like, this reduces the goal of proving Q to proving P. That's what the apply tactic does. My experience is that out of intro, exact and apply, Lean learners find apply by far the hardest. And I think that's because it's arguing backwards. So after apply H, the goal has changed. The goal is now P, but that's one of our hypotheses. So we can do exact HP. And there we go. We've got goals accomplished. And we're back to 11. We're back to 11 warnings, which are the 11, the 11 problems on this problem sheet. So that's the end of this video. So as I say, it's sort of spoiler free. But in the next video, I'm going to go through and I'll show you how to do. I'll show you the solutions or my solutions to the problems on this problem sheet.